Hello, in this video we're going to look at the Nobel Prize in Physics for the year 1904, won by John W. Strutt, Lord Rayleigh, for his investigations of the densities of the most important gases and for his discovery of argon in connection with these studies. Here you see an apparatus used to investigate argon. I'm not sure whether it's actually used by Lord Rayleigh. This is the Nobel Prize lecture's name, the density of gases in the air and the discovery of argon. This lecture is summarized by me. In reality, it's a bit longer. We start with the redetermination of the density of gases in relation to Proud's law. Best results, experimental results that is, are those of Rayleigh, and then the density of argon was 15.969 times that of hydrogen. In mine and Cook's work, Raygleigh's method was followed. The working globe was counterpoised by a dummy globe of the external volume. In the globe, of course, is the gas. It's surrounded, it's closed. This made us independent of fluctuations of the atmosphere's density. Cook's result was practically identical with that of Rayleigh, but the correction was overlooked. It was assumed that the external volume of the working globe was the same whether aqueous or charged to the atmospheric pressure. The volume must be greater in the latter case. The correction reduced Cook's to that of mine, 15.88. Discrepancy from Proud's law was thus increased. Then nitrogen, using Harcourt's method, another experimentalist, recommended by Ramsay. After a series, I reflected that the method which I had used was not Raygleigh's. It was desirable to multiply methods, so I used a more orthodox pressure. Ammonia being dispensed with, air passes directly over hot copper. Again, a series in good agreement with itself resulted, but the densities obtained by the two methods differed by 1,000 parts. This is a small difference, but beyond experimental errors. The amnesia method gave the smaller density. Can the difference be attributed to impurities? The answer was no. What was the difference between the two kinds of nitrogen? The one was derived from air, the other about 1/5 part from ammonia. The most promising course for magnifying the discrepancy applied to substitute argon for air in the ammonia method, so that all the nitrogen should be, in that case, be derived from ammonia. Success was attained, the nitrogen from the ammonia being now 100 parts lighter than that from air. The discrepancy was increased, as was expected. Among the explanations were the presence of a gas heavier than nitrogen in the air, or the existence in the ammonia prepared gas of nitrogen in a dissociated state. Since this dissociated nitrogen would probably be unstable, a sample was kept for 8 months and the density was unaltered. So this is disproved. On that, the air-derived gas was heavier than the chemical nitrogen on account of the existence in the atmosphere of an unknown ingredient, the other option. Next step, the isolation of this ingredient by absorption of the nitrogen, a difficult task undertaken by Ramsay and myself. Two methods. The first, that by which Cavendish had originally established the identity of the principal component of the atmosphere with the nitrogen of nitre. The other, to absorb the nitrogen by means of magnesium at a full red heat. In both these ways, a gas was isolated of amount equal to about 1% of the atmosphere by volume and having a density about half as great again as that of nitrogen. It was proved to be non-oxidizable, refused absorption by magnesium at red heat, and refused any chemical combination. The name argon was given. The most remarkable feature of the gas was the ratio of its specific heat, the highest possible, 1.67. Ramsay and Trevor discovered small quantities of new gases contained in the aggregate named argon. Helium, originally obtained by Ramsay from cleveite, is present in minute quantity. Experiments upon the fractivity and viscosity of argon revealed nothing remarkable, but the refractivity of helium proved to be unexpectedly low, not attaining 1/3 of that of hydrogen, the lowest then known. The preparation of argon begins with liquid air. Argon, being immediate in volatility, may be expected to increase relatively to nitrogen, though it was decreased relatively to the oxygen. A number of analyses for oxygen and argon as evaporation proceeded are appended. See table 1. That's at the end. I can show you that. Here it is. If you want to study it, pause the video or go to the original lecture. Also possible, of course. Okay, going back. Okay, again, a number of analyses for oxygen and argon as evaporation proceeded are appended. Table 1. They relate to the vapor arising from the liquid and not to the liquid itself. It's an advantage starting with liquid air, then eliminating the nitrogen. Where there is a supply of alternating current, the method of oxidation is more convenient. It is an advantage to retain the oxygen. If the oxygen content be about 60%, the proportion is about sufficient to oxidize the nitrogen. We may compare this with the mixture of atmospheric air and oxygen, which behaves in the same manner. In the latter, the proportion of argon would be reduced from 2% to about 0.4%. The advantages of using liquid air is thus 5 times. The mixed gases were absorbed with 20 liters per hour, and in the alternative method the nitrogen is absorbed by magnesium or calcium. In this case, it is necessary to remove the oxygen. On this view and on the supposition that liquid air is available in large quantities, it's advantage to allow the evaporation to proceed at great lengths. A 20% mixture of argon and nitrogen is readily obtained. The preparation of considerable quantity of argon is rather an undertaking. There's no difficulty in demonstrating its existence. By the use of a specially shaped tube and an induction coil actuated by a small growth battery, I showed the characteristic spectrum of argon at atmospheric pressure, starting with 5 cc of air. Here it is, the spectrum of argon. Every element has its own spectrum, as you probably know. Another question relating to the gases of the atmosphere, the amount of free hydrogen. Goethe announced that the amount of free hydrogen reached 2 divided by 10,000 in addition to variable quantities of hydrocarbons. My own observation related to the visibility of the sea line in the sparks then taken through carefully dried air and atmospheric pressures. This line could never be entirely eliminated, but could be made somewhat faint. When air to which 1/1000th of hydrogen had been added was substituted for pure air, the visibility of the sea line was increased. The difference was such that one might believe that the proportion of hydrogen actually operative was doubled. In accordance with Gautier, could we assume that the smaller quantity of hydrogen really accompanied the air? Observation rendered this doubtful. The visibility of the sea line, which ordinary air was not perceptibly diminished by the passage of air over red-hot copper oxide, I found on a former occasion that hydrogen introduced into nitrogen could be so far removed in this way that the density remained sensibly unaffected, although 1/1000th of the residual hydrogen might be expected to manifest itself. When air purposely contaminated as above with 1/1000th of hydrogen was passed over the copper oxide, the additional hydrogen appeared to be removed, the visibility of the sea line reducing itself to that corresponding to untreated air. Spectroscopic experiments were made in which the platinum points were replaced by points of aluminium. The evidence could hardly be reconciled with. I was accordingly induced to make determinations by direct combustion. 10 liters of fresh country air dried as thoroughly as possible were passed over copper oxide at a red heat. The gaining weight of a phosphoric tube through which the air subsequently passed indicated an amount of free hydrogen corresponding to only 1/7 of that recorded by Gautier, though no allowance to be made for the presence of hydrocarbons. This is not due to faulty manipulation. The question is as to the efficiency of the copper oxide. Did my furnace tube allow the main parts of the free hydrogen to pass unburned? This is very unlikely. It is possible to examine the effect of small addition of hydrogen to air. The added hydrogen was only 1 cc, thus 1,000 by volume, or half the quantity originally present according to Gautier. Hey, this is a little strange line. The hydrogen was first diluted in a gas pipette with about 100 cc of air and allowed time to diffuse. The 10-liter aspirating bottle being initially full of water, diluted hydrogen was introduced at the top and was followed by 10 liters of air from the opening, after which the mixture stood overnight, sufficient to assure a complete mixture. The result shows an additional gain of 0.00072 grams, very nearly the full amount, 0.00075, corresponding to the 1 cc of added hydrogen. We may say then that the copper oxide was competent to count for a small addition of hydrogen to air. Another branch of my work upon gases has relation to the law of pressure, especially low pressures. Usual methods are deficient in accuracy. Amagat considered that under the best condition it is not possible to answer for anything less than 0.01 millimeter of mercury, that's pressure, by the use of a special manometer was able to carry the accuracy at least 15 times further. Thus to investigate with accuracy the effect of pressure not exceeding 0.0 millimeter mercury. Boyle's law was fully verified even in the case of oxygen, for which C. Bauer had found abnormalities. I investigated the compressibility of gases between half and 1 atmosphere of pressure. In table C2 gives a summary of the results for various gases. Here it is. If you study it, stop the video. And especially here, it's B is important. That is pressure times volume at half an atmosphere divided by pressure at volume at 1 atmosphere. That's the B value. Table 2 gives a summary of the results for various gases. The temperature being the same at both pressure and having the value recorded. The B should be less than the unity in the case of hydrogen and exceeds that value for the other gases, is what to be expected from the known behavior at higher pressure. The principal interest of these results is perhaps to calculate corrections to ratio of densities as found at atmospheric pressure, so that to infer what the ratios would be in a state of great rarefaction. It's only under this condition that Avogadro's law can be expected to apply accurately, as I pointed out in my 1892 in connection with oxygen and hydrogen, and for nitrogen and oxygen. The connection is not important. The original comparisons of densities is unaffected. The atomic weight of nitrogen is found to be 14.01 and not 14.05 as found by Stes, another experimentalist who also got a Nobel Prize a little later. Well, here again you see the two tables which is referred to in the text. If you want to study them, stop the video or click at the link. This link is also in the description of the video. Then you can go to the original lecture, which is of course not summarized and thus has more arguments. Concluding, here you see a piece of frozen argon, which every gas can be liquefied and frozen. And here you see argon in probably a more familiar setting in a tube, in a discharge tube, giving a specific light, which is a sort of pink, as you can see. Well, this was it. As said, this is a summary, of course, from the lecture. There's also another video more in general. If you want to study more, you can go to the official Nobel Prize site where all this information in the end is coming from, summarized by me. But there you can see the complete lectures, also the award prize ceremony, speeches, biographical information, etc., etc., etc. For now, thank you for watching and maybe until another time.